All right, so today we're going to talk about the fundamental theorem of algebra, which includes complex numbers, which is something that you learn in Algebra 2. Okay, your imaginary numbers you learn in Algebra 2. Do you know why you learn them and what you use them for? No, okay, because in Algebra 2, the best we can do in Algebra 2 is this is what they are, and you have to trust us because this is as much as we can do right now, especially in the amount of time that they have to do it with them, to work on that with you. Even in pre-cal, we're not necessarily going to apply them a lot, or at all, really. You don't really apply them that much until you get into calculus, but I want you to understand kind of where they're coming from. So do you remember in geometry when we graphed some things and shaded a region, and then we revolved that region and got three-dimensional shapes? Remember doing that? So we had to talk about how we were graphing on the coordinate plane, and you could graph these lines and you end up with like a rectangle. So then when we revolve the rectangle, it like comes out off of your paper and revolves down and ends up making a cylinder. Remember doing that? So that's your 3D graphing, and when you graph things in 3D, you get an axis that would stick out on my board like this, which would be called your z-axis. Does that make sense to you? Okay, so that's where your imaginary numbers live, is on that z-axis. So you've got the x and the y and then the z-axis, and your imaginary numbers are actually, when you have like 2 plus 3i, that's actually an ordered pair that you would go and plot. You go to 2 and then 3i out on the z-axis. So I'm going to show you 2 minutes of a specific video. There's about 5 videos in this series. They're only like 5 minutes a piece, each one of them. And there's a lot of math videos that explain things that are terribly boring. Even if it's like semi-interesting, it's still just like deathly boring. You know, we just want them to get to the point. But these are pretty short, and I'm not going to show you all of them. I'm only going to show you 2 minutes of one of them. But they're all in this little series that if you're going to be in Calculus BC next year, being able to wrap your mind around this a little bit more right now would really benefit you. So it may be something that you want to go back and you want to kind of watch to see if you can make it make a little bit more sense to you. I'll put either, I don't know if I can put a playlist within my playlist. If not, I'll give you the link to the playlist somehow, so that if you want to go back and watch them and kind of wrap your mind around it, you can. So like I said, I'm just going to show you 2 minutes of this. That is not what I wanted. Right here.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension.
Okay, so this 3-dimensional type graphing, you're going to see a lot of graphs like that in calculus because you start to revolve more things and you're looking for area and volume and whatnot. But that's partly how we start to apply those and where the imaginary numbers actually live. And why? And I just want you to know that there's more to it than just because we can find it and call it I. Okay, but we can't really give you a whole lot more in depth with that yet, because you need more math behind it for it to start to make sense. Just know that it is out there and it's stuff that you kind of haven't done yet. Things start to get like kind of weird, but also pretty cool when you learn why everything works. All right, so let's look back at, you're here, we're going to go on page 58. So Fundamental Theorem of Algebra, page 58. So we're going to start with a quick little review of finding our complex numbers. And, well, also, when he said in there, when you do that, you have the x squared plus 1 equals 0, and so you should have two solutions. But when you graph it, it doesn't cross the x-axis, so we say no solution. You're not really supposed to say no solution, right? What do you really say there? No real solutions, exactly. Because it does have two solutions, it just doesn't have any real solutions. So that's where those clarifying words become very, very important, because there's a big difference there. So there is solutions, they're just not real solutions. All right, so it says, just as a polynomial function can have real zeros, rational or irrational, it can also have complex zeros. Find all the zeros of the polynomial function. So we're going to start off factoring this just like we would factor, right? And since this is a fourth degree, but it's set up like a quadratic, so I should hopefully be able to get something factored here. So if this factors, then this is x squared, and this is x squared. And then what are my other two numbers? -6 and +2. Oops. And then, can I factor this anymore? No. Okay. Now, the answer to that is really yes, and I should have worded some other stuff differently the other day. We can factor it more, and we will factor it more, not right this second. We can't factor it anymore using the factoring skills that we have and that we use on a normal basis, all right? But we will end up factoring this completely in just a minute. But right now, all this asks us for are the solutions, right? All of them. And so at this point, because I'm not capable of factoring it anymore right now, we're going to do pretty much what we did yesterday. So this is going to give me that x squared minus 6 equals 0. So x squared equals 6. So x equals what? Plus or minus square root of 6, right? Not an imaginary number, just an irrational number, right? Then here I have x squared plus 2 equals 0. So x squared equals -2. So x equals plus or minus the square root of -2. But are you allowed to leave it like that? No. That's really like -1 times 2 in there, right? What do we use for the square root of -1? I. And then can I do anything with the square root of 2? No. So it's just I times the square root of 2. Plus or minus, yes. So x is equal to, my x's, my solutions then, are plus or minus the square root of 6 and plus or minus I times the square root of 2. So I have 4 solutions. That's a fourth degree. Only 2 real ones and 2 imaginary ones. No rational ones, but these are both irrational. Okay, everybody good? Like this is stuff we can do, right? All right. So let's go ahead and I want you to go ahead and factor number 2. Now, if you can factor that just fine, which you should be able to, you can knock yourself out and just ignore me. But I'm going to walk you through grouping one last time, and if you still can't factor it, you're on your own at that point. But if you don't want to do grouping, or you don't even need to, you can just tune me out and factor it yourself. Okay? So if I'm going to do this by grouping, 4 times -8 is -32. So I need 2 numbers that multiply to give me -32 and would combine to give me, oh, this should be 4x to the 4th. I'm sorry. My 4 disappeared. Yeah, there you go. That makes more sense now, right? Sorry about that. I even thought I checked because I knew it had moved. I don't know what happened to it. It completely disappeared. So 4x to the 4th. I'm so sorry. All right. So now I'm going to do it by grouping. Okay. -32. So this is going to stay 4x to the 4th, right? And then this would be 1 and 32. So it's going to be a positive 32x squared minus x squared and then minus 8. So if you're going to do this by grouping, you have to split that middle term so you actually have 4 terms there. Then I would factor out of these first 2. I'm going to get 4x squared. That leaves me with x squared plus 8. Out of these 2, I'm going to factor out a negative. That leaves me with x squared plus 8. And then this is going to give me 4x squared minus 1 times x squared plus 8. And you get to this point, however you may get to this point. Can I factor it some more? Yes. What is this called right here? Difference of squares. So f of x is equal to 2x plus 1 2x minus 1, and then x squared plus 8. Okay. So that's as much as I can factor right now at this moment. But I can find my solutions here. So here this is x equals negative 1/2, x equals 1/2, x squared equals negative 8. So x equals plus or minus the square root of negative 8. Can I simplify the 8? Okay, what comes out when I simplify it? 2, and then the I with the negative. Good. So x is equal to plus or minus 2I square root of 2. So my zeros then, plus or minus 1/2, and plus or minus 2I square root of 2. Okay. Everybody good with all that? Any questions? All right, we're going to skip number 3. Move on to number 4. So what can I factor out here? Negative 2. So I take out the negative 2, and this gives me x cubed plus 8. Can you factor that? Yes. So go ahead and factor that. Good. Thank you. I'll try. That's what I want you to do. So here's what we should know. If it's the sum of cubes, right, you're going to get a binomial and a trinomial. The numbers in the binomial are the cube root of these two. So the cube root of x cubed is x, cube root of 8 is 2. Then the signs are the same, opposite, always positive. This one right here is x squared. Then you multiply the 2 together and you get 2x there. You square that and you get 4. Okay? So if you learn how, if you can't just do it from left to right, if you learn how to build it, that's when you understand the concepts, you can do it a piece at a time, even if it's kind of from the inside out. All right, can I factor this anymore? No. So not at this point. It is factored as much as I can factor it. So then I need to find my solutions here. Now, is this negative 2 that's hanging out front going to affect my solutions at all? No, it doesn't. But if it's supposed to be fully factored and I drop him off, I'm wrong, okay, because he does do something to my graph. But I only have to find these two here. So this is x equals negative 2. I couldn't factor this anymore, and so what should I do here? Quadratic formula. So x equals negative b, which would be a positive 2, plus or minus the square root of b squared minus 4 times a times c, all over 2a. Especially on things like this, first step should be 0 work, because if a mistake is going to be made here, it is most likely going to be some sort of sign error, not that you completely don't understand or that you can't multiply. It's some stupid mistake because you didn't write stuff down and you were trying to do too much in your head. So this gives me 2 plus or minus the square root. 2 squared is 4, minus 16 would be negative 12 all over 2. At this point, can I reduce this 2 with anything? Not yet, but I might be able to. So I know that that negative is going to come out as an I, and when I simplify the square root of 12, what does that become? 2I square root of 3. Yeah. 2 squared of 3 is 12, though. Yeah. Don't forget your I, all over 2. Now can I simplify it? Yes, so now I can cancel those i's out, and I get that x, not the I, I'm sorry, cancel the 2's out. So does that just leave me with I times the square root of 3? No. This doesn't cancel out and completely go away, right? I still have 1 plus or minus I times the square root of 3. So my zeros in the end then are negative 2 and 1 plus or minus I times the square root of 3. Are we good? Okay, so that's your crash course review in complex numbers. Should not be brand new information to you, right? Alrighty, so let's talk about the fundamental theorem of algebra. Fundamental theorem of algebra says a polynomial function of degree n, where n is greater than or equal to 1, has at least 1 0 in the complex number system. at least one 0 in the complex number system. Then there's a little clarifier here. Any real number is also a complex number. That does not say any real number is also an imaginary number. Those are two different things. Okay, so I want to show you this graphic here. It's a little Venn diagram of the number systems. So the big all-encompassing one is complex numbers. They can be written as a plus bi. Within this system lives imaginary numbers. That's a plus bi, where b is not equal to 0. That's where you get the I from, right? When you talk about real numbers, then the b is 0. Okay, so 2 is a complex number. It's 2 plus 0i. We just don't worry about the 0i part of it. Does that make sense to you? So when it says they at least one in the complex number system, well, really that's all numbers that you understand. Okay, and they can all be written as this. We just don't bother when b is 0, because what's the point, right? And then here's how the rest of them live, so you know what's what there. Okay, and then so we've got imaginary numbers. That's when you actually have a number with the I. And then a pure imaginary number, your a would be 0. So like 2i is a pure imaginary number. 3 plus 2i is just an imaginary number. Okay, so good. Yes, pure imagination. All right, so then we had the linear factorization theorem, which we have already looked at once, but we weren't talking about complex numbers at this point. It says if c is a complex 0 of a polynomial function, then x minus c is a linear factor of the polynomial. Here's where some more clarifying comes in. It says this means that all polynomial functions can be completely factored. Okay, so when we say we can't factor it anymore, not 100% true. It's that we can't factor it using the traditional factoring that we've been using. Okay, but we will be able to completely factor everything. Okay, we all good? Questions? All right. So we're going to find the zeros of the function, which is what we did on the front, and then we're going to use that to do the complete factorization. So we're going to start off the same way we started off on the front by just finding the zeros. So I can start, this is a 4th degree, and I can treat it like a quadratic. So this is going to be x squared and x squared. And then this is negative, so my signs are opposite. So what could I put in this first one? X squared what? Minus 25, and x squared less 1. Okay? And double check it that it actually multiplies back. Not just that these two numbers multiply to give you this, but that when you do the inside and the outside, you also get that. Can I factor this a little bit more? Yes. So this is going to become x plus 5, x minus 5, and then x squared plus 1. We have been saying we can't factor it anymore. We can. We just need to x squared. We can. All right, so I need to find my zeros here, because that was the first part of the directions. So x equals negative 5, x equals 5, and then x squared equals negative 1. So x equals plus or minus what? I. Okay, everybody good with all that? So our zeros are plus or minus 5 and plus or minus I. Okay, everybody good? That's as far as we got on the front. That's, hey, I found them. They're imaginary. I don't know what to do with them, but I can find them. And then we factor it completely. Well, we already have two of the factors we know to use. F of x would be equal to x plus 5 times x minus 5. And that's where these are coming from, right? Which means this is going to give me x minus I and x plus I. Or plus and minus, it doesn't matter. That is my complete factorization. Just like that.
So that's all we're doing.
That's all you're doing. That's it, completely factored. We're not going to graph them right now. We're not doing anything else. But that's how we're going to get it completely factored. Okay? We all good with that? Easy enough? So it's just like one more step. You just got to be careful with that one more step a little bit. All right, let's go ahead and do number 2. Now, number 2 is the same equation as number 1 on the front, but that's fine. So we should be able to fly. We've already factored it. X squared, and it was minus 6 and plus 2. Right? And then we found our zeros, so x squared equals 6. So x equals plus or minus square root of 6. X squared equals negative 2. So x equals plus or minus I times the square root of 2. Okay. So we did that. That was number 1, I think, on the front. So my zeros then were plus or minus square root of 6 plus or minus I times the square root of 2. I'll just get it all rewritten. So then we just take it one more step, and we use those to factor. So f of x would be equal to x plus square root of 6, x minus square root of 6, x plus I square root of 2, and x minus I square root of 2. And if I multiply it all back, I should get what I had originally. Okay? Any questions at all at this point? We good? All right. So I want you to work on number 3. Go ahead and get it factored and get as far as you can. So does everybody agree with me up to this point at least? Okay. So when I go in here to write in my factors, oh, hang on, let me make myself some more room here. Actually, I write too big. When I write these in, am I going to put x plus 1/3 and x minus 1/3 in here? The answer to that is no. You don't get to always just take them right out of this set and plop them down right in here. Because if I did that and I had x minus 1/3, x plus 1/3, and then x plus 2i, x minus 2i, when I multiply it all back together, am I going to get this? Because where would that 9 come from, right? So here's the thing. If I did that and I multiplied it all back together, the equation that I would get would have fractions in it. And for it to be a polynomial, the coefficients have to be integers, so it wouldn't qualify. I would have to clear my fractions. Once I cleared my fractions, I would end up with that. So it's not that my answers are wrong. The problem is this. If you want to think about, so like up here, when let me see. Okay, so let's just take one of these up here. And I said, all right, well, I know that x equals -5. Well, to get the factor that I actually put into my little equation up here, I add 5 to both sides, and that's where I get my x plus 5 equals 0 from, right? That's how I get it. Just move it back over. So when I have here, if I have x equals -1/3, well, I can do the same thing, and it is true that x plus 1/3 would equal 0, okay? However, this is not, I don't want fractions in there. Irrational numbers are okay, complex numbers are, all that stuff's okay. This is not okay. The other way I can get there is to multiply both sides by 3 and then add my 1, I get there. Now, I'm not saying you have to go through this. What I am saying is, well, we already had this. You won't necessarily always have that in front of you because you may be given a list of factors. You have to think about where it came from. Like, how would you get that number from a factor? And then, so what ends up really going here is going to be x. Oh, no, I'm sorry, not x. I'm doing that wrong. This 1/3 is going to give me 3x plus 1 and 3x minus 1. Because once I set those equal to 0, that's where that is coming from. Does that make sense to you? So you have to be careful when they're fractions to make sure you're truly putting in the right thing. And then x plus 2i and x minus 2i. And then that is my fully factored form with my zeros. Okay, everybody good so far? All right, so we're going to skip number 4, go on to, and I want you to do number 5. So when you're done, take a look and see if you agree with me. I don't know that we necessarily needed to do another example, but I did want there to be at least one on here where you actually had to use grouping, and also so that you know you could just have one plain old normal looking factor in there, and that's fine too. They don't all have to be all weird. Okay. Any questions at all? Are we good? All right, so go ahead and glue it in now so you're not trying to scramble to do it at the last minute. You have a lot of time to work, so make sure you make a good use of that time.